My name is Radhika and my project is an image-based jigsaw puzzle solver. So it's an iPhone app. So the aim is that the user will take a picture of the scattered jigsaw puzzle pieces, and the application is supposed to return the solved picture to the user. So as you can see that I have laid out scattered puzzle pieces on blackboard. The assembly uses a black background. So as you can see, this is the app. So you can either pick image from a library or you can capture image from a library. If you choose to pick image, you can pick whichever image which is already captured, and then if you press the button solve it, it will solve the pieces. Now because of the reassembly, the picture is a little smaller. You can actually crop it and then rotate it to see that it actually matches the original picture that it was supposed to be. Or you can either capture it or you can take select it from a library and it'll give you the solved puzzle. So it's a computer vision application for an iPhone. Thank you.
All right, so this is my project, which is a hybrid fiber optic LED lighting system. Basically the way it works is there is a collector on the roof of a building that follows the sun, funnels light into fiber optic cables, and redelivers it inside in light fixtures. The light fixtures are also equipped with color-tuned LEDs that match the color of light outside and mimic it inside so that you get the most coherent light source possible. It saves a tremendous amount of energy and also has human health benefits, including improving circadian health, reducing seasonal affective disorder and depression, and making you more alert. And the whole system can be controlled from your smartphone.
In our project, we are using Microsoft Kinect Sensors to generate an accurate 3D map of an indoor scene. So Microsoft Kinect Sensor have 3 cameras. This is a Microsoft Kinect Sensor. It has 3 cameras, one for RGB camera, and the other 2 can be used as 3D depth sensors. And we will get sequence of images from this sensor, and we will align the later image to the previous one to do 3D reconstruction. So once we get the image from Kinect Sensor, we'll change it to a point cloud using point cloud library. And in order to achieve 3D reconstruction, we are using an algorithm called iterative closed point algorithm. In this algorithm, we assume there are 2 surfaces, one for source surface and one for destination surface. So the destination surface can respond to later images, and the source surface can correspond to the previous images. And in our algorithm, the input will be 2 row scan from the Kinect sensors, and the output will be a refined translation and rotation of these images.
Towards the end, plan to go to Arizona.
So this project is a project that we worked on for our 4760 class last semester. This was our final project, and it's Taiko drum Sensei, so it's a teaching tool for beginners who are starting to play this particular style of drumming. And the device that we built is a board that clips onto the head of the drum, and it's supposed to be able to pick up different types of hits, so just a soft hit, a loud hit, and a rim shot hit. And the idea is you have these clipped onto multiple drums, and in a group setting we'll be able to tell you whether everyone's playing on beat and how off everyone is from each other. So this drum in particular, in this board, these 3 LEDs will tell you what type of hit you're having. So we have a soft hit with a green LED, a loud hit, and then a rim shot hit. Let me see.
Soft hits.
So these are soft hits, and then loud hits, and then rim shots. and each board has two piezo sensors. It has the microcontroller, a couple buttons for control, and then a infrared transceiver so that the boards can communicate with each other. Some of the features that we added were just simple metronome, so I can set a tempo, and a blue LED will just keep blinking at the tempo. Another feature is a follow the leader mode, which is
like, say like I'm the teacher board and he's the student board, so I'll just start playing, set a pace, and it will tell him if he's going too fast, too slow, if he's hitting the right beat, you know, that kind of thing. So if I just start playing.
So here it's telling me that I missed the hits, and then if I should, and then the blue LED is telling me that we're both playing it together, and the green or yellow will tell me if I'm too fast or too slow. So that's just the basic idea between these boards, and it's just a teaching tool.
So for our project, we were trying to make a safe way of testing someone's heart rate and getting their ECG signal. And so what we did was we actually built a circuit that can, just when you touch the metal bars, you can actually calculate someone's heart rate and also get their beats on this oscilloscope. And our circuit actually is here, and what we did was it's completely safe. So at the beginning of the circuit we have capacitors, which helps for DC isolation, and also we have resistors, which limits the current. So that's our conditioning stage. And then afterwards we have a gain stage with a differential amplifier, and then we have more filters and other gains to just amplify the signal so it's stronger, so we can detect it on the oscilloscope. After that we passed it into the NIDAC and then did some digital filtering, which unfortunately isn't here right now just because we didn't have a computer to bring that had the licensing for the NIDAC materials. But just to demo it really quick, Sean, my partner, will take the metal bars.
Yeah, so just hold them gently in your hands, and so there's a little bit of wandering, but once we get that into the MATLAB and run it through the digital processing, we can clean that up. And as you can see kind of on our poster, we have some screenshots. This is just our MATLAB GUI. Basically it's got a bunch of different things you can do. One is change the filter cutoffs. So as you can see, this is a signal from me, and then we adjusted the filter cutoffs and it cleans it up a lot. And you can see how that can be easily thresholded to calculate beats per minute. So that's how we did that. And then one thing that we thought was really cool from all of it is this is my heart beat averaged over, you know, 5 to 10 beats. And when you compare it next to like kind of the standard accepted QRS complex image, you can see every wave, including the P and the T waves. So we thought that was pretty neat.
And then our purposes for doing this is just hopefully for like educational purposes. So then for introductory EE classes or classes that are doing BME and electronic devices, it's a really simple and safe way of students to do it in lab.
Building something that's actually interesting and cool. Once you have it completed, you have some, you know, tangible that you can look at and say, here's what I made.
Planar images such as books, paintings, icons on your smartphones, and logos are very common in real world, and it is very significant to recognize this kind of planar images. So in our project, we developed an application on iPhone to recognize planar images. There are two main parts in our project. The first one is the feature matching. So for each image, we can use ORB algorithm to compute the key points like this. And then we do this kind of matching between the key points to key points. But you can see at first that the matching results is not as good as we expected. So we do some kind of optimization and got this kind of results. It's pretty good. After we have these good matches and key points, we can compute the homography and compose the homography into rotation matrix. That is, we can know how much your image is rotated from the front view. And the iPhones are equipped with accelerometers, which can tell us that how much the camera is rotated from the gravity. So combine these two things, we are able to compute the orientation of the image with respect to the ground. In our demos, we have these three images in our database, and we have two demos. The first one is a rolling cube. We added a 3D cube that rolls from the top center to the bottom center of the image. And in the second demo, we have a a colorful boundary whose color is changing with respect to the angle of the image. So when the angle is pretty small, the boundary of the image is right, and when you increase the angle, it becomes green and blue, and so on.
So what I created was a autonomous quadcopter docking system. What inspired me is that quadcopters are really interesting. You can do a lot of unmanned missions. You can do surveillance in areas that humans can't access. Unfortunately, their main limiting factor right now is that they have very short battery lives. Even with a quadcopter like this, you only get about 7 minutes of battery life, which is not much to do anything. So my idea was to try and come up with some system that the quadcopter could autonomously find a place where it could be recharged and land. So what I ended up implementing was a system such that the quadcopter uses a old Android phone and computer vision to look for a target, which in this case is just a simple red square, and when it's overhead the target and centered on it, it will initiate an autonomous land. The system is fairly simplistic compared to other quadcopter devices. However, its main advantage is that it uses completely open source parts and all things that are off the shelf, so any hobbyist or student or researcher could pick these up and work on it themselves. There's nothing proprietary about it. All the software could be hacked and modified and used for whatever you want. So I'm using a kit that you can purchase commercially, an old phone, which most people have already, an RC controller, which is without using an RC controller, instead using a gaming controller to emulate that, and this open software such as MapProxy and Mavlink, which are Python implementations of controlling software for autonomous vehicles. So what this allows you to do is anyone could work on this type of project and make a difference.
So essentially we made a microphone using a laser, and the way that it works is you reflect it off a piece of glass. The piece of glass can be anything from a window to like the surface of a building, just any reflective surface, and it reflects back to this photo transistor over here, and it goes through amplification and filtering, and you can actually listen to it using headphones. And so ideally you can hear what people are saying or speaking, or what's happening on the other side of a piece of glass. Or we also theorize that it could be used with construction purposes and building frequencies and resonance. And so that's the analog portion of our project. We also have this microcontroller which performs a fast Fourier transform and displays the audio spectrum.
So first, our project was composed by LED hardware system and the software part of the control system. The control system is on a cell phone, and this is an Android application phone that user could control our LED lightings through the application. And the idea is that when they try to scroll a bar of each LED color, and the command will send to the Arduino board, and the Arduino board will then have the command to our LED systems, and then user can adjust the current, the brightness of the LED. And so let's discuss about how we design our LED system.
Okay, so the other part of this project was to actually get a better spectrum of light than the white light that you usually get from commercial lighting. Now, we did measurements with a spectrometer, and the white fluorescent light is just noise. It has three very narrow peaks, which is red, green, and blue, and that's like the basic thing you need for light. So we actually designed this integrated board, which combines 5 different colors to produce a better spectrum of light. These LEDs are very high power. They can produce a lot of light, which I will demonstrate shortly. The circuit itself consists of a control unit which controls the current that goes through, because there is a threshold of optimal operation which goes from 500 to 700 milliamps. If it goes more than that, it can burn the circuit. So what this does is that if the voltage gets increased, then the current gets controlled. Now I will demonstrate the amount of light that you can get out of this circuit. And if you actually point it to someone or something, you can see the spectrum of light. You can see how everything gets more natural hue, and all the colors get. You can tell the red is really red, the pink is really pink, more so than with regular fluorescent light.
Okay, so our project is basically sustainable data centers, where we're trying to reduce the energy consumption in data centers of Verizon. So we're building a small-scale data center in lab, which simulates the heat output of a real-time data center. And this is going to be the small-scale version of the server racks. And we're building a data acquisition system which collects real-time data and sends it to a database which logs the data, and the user can take appropriate action depending upon the activity of the data center. So if the temperature is too high, then he can control the fan speed and accordingly take action so that they can reduce the energy consumption. And coming to the different teams, sub-teams involved, this is the hardware PCB design team which developed this PCB for the server racks for the data acquisition system. And there's going to be a firmware development team which basically develops a firmware for the communication between the wireless communication between the end device and a central coordinator system. And there's a database development team which develops the data logging system and the graphical user interface, which presents data in the form of graphs to the user. So this is one of them, which shows how the temperature is changing or varying over a period of 1.5 minutes. And yeah, that's about it. In the end, we would like to develop a complete version where the user will be able to send commands to the particular end device or receive commands from the end device to take some action, and the control will be executed at that point of time. But right now it's just the basic firmware that we built. So thank you.
All right. So we are part of the Cornell Cup USA project team. Our job is as a support group for this competition called Cornell Cup USA presented by Intel. It's a joint competition on embedded design founded by Intel and Cornell about 2 years ago. So our main job is to develop a base platform for other teams and other schools to use, because most teams entering the competition are 3 to 5 people, and they may be, say, all CS students, so they don't know how to set up, say, electrical systems for their design. And what we do is just build this a base robot. We call it the Mod Bot. This year's version is called the Juna Bot. So it's basically taking a bunch of various systems, mechanical, CS, and electrical, and putting them together. And what we do is we pass the documentation to different teams so that they can say, if you needed like a power system, you can take our power board and get regulated 5-volt and 12-volt outputs from it. We actually printed about 100 of these and brought them to the competition. There's a lot of what we saw was a lot of students were, say, running off lead-acid batteries or various things and then just plugging into their system, and it's very unsafe. So we developed this whole power solution for them, so they can just cleanly run power for whatever application they want to do. And that's kind of the idea behind the entire project, is to build a large system, but that can also be, that's very modular and broken down. So like mechanically, we have this T-bar that it can mount things off of. So if a team wants to make some sort of mechanical construct, they can use T-bar to use a mix. And that's kind of our idea behind the Rock Band bots. So these robots can play the Rock Band video game. And the main idea was, say, we can take our system here, reconfigure it, make something completely different, and just to display the modularity of the device. So yeah, these robots play Rock Band and also have little autonomous motion. And that's basically our project. We just came back from Disney World about 2 days ago, where the competition was. And we just showed off our robots. They can play. We put a little chair, that's an example application, so they can play laser tag. So we had a little field set up where we run around and play laser tag with other teams. There's a lot of other subsystems in here. The FPGA system, which handles local positioning, taking in GPS, accelerometer, gyroscope, and magnetometer data, and positioning the robot outside. There's the motor control sub-team. And then on the CS side, there's also a lot of communications, networking, GUI work, and all of those things can be broken down in our documentation and given to students so that they can apply it to whatever project they're working on.
So our project is to make sure that we're able to track users within the building. The current way the building heating and cooling works currently is we don't take into account the user occupancy information. So with our project, we want to make sure that we get around this problem by tracking each and every user's smartphone. So the smartphone sends its its location to the backend server. So the server uses a weighted centroid algorithm to determine where exactly the user is within the building. And the server can cluster these results and provide a summary of these results to the HVAC systems, telling that in a given room there are 10 users at this point of time, and the set temperature should be X as opposed to Y. So our project is to make sure that the user tracking location works. So in order to do that, we basically send the signal strength value of all the routers that a user that a user's smartphone can see at a point of time. So based on this signal strength, the server determines the location where the user is. We ran this test data for Philips 314, Philips third floor Philips. So here we can see the user has been, the location of the user has been tracked. So we can see the user is stationary. So now the user is moving. So here we'll be able to track the user movement within the building. Sure. Hi, I'm Abhijit. I'm a master's student here with the ECE. So my contribution for the project is I was responsible for the Android application, and I'll pass on the mic to the next teammate.
Hi, my name is Fei Fei. I'm also a ECE student here, and I'm responsible for the iOS application in this project.
Hi, my name is Peng Tian, and I'm also an MN student, so I'm working on the server programming development.
Hello, my name is Xiaolei Shi, and I'm in charge of the HY control system development and the MPC algorithm development, and also the MN student.